Hey, good morning. This is for everyone who did not get to view the live lesson, or for anyone who just wants to hear the live lesson differently. So, like without all the student interruptions, and I'll probably honestly get through more on this video than we will on the live lesson, since I'm doing it first. So, we're gonna, by popular demand, sort of review the same types of problems that were on the previous couple days worth of stuff. I know Friday's lesson really threw everyone for a loop, and I apologize for that. That wasn't really my intention. But keep in mind, 70 minutes max. Do not go more than normal class time. Don't drive yourself crazy. Just reach out and say, hey, didn't finish. I spent the time. I'm going to ask you questions. That's fine. That's what I need from you. Okay? There's always revisions. I'm revising as I go, so just bear that in mind. Don't stress yourself out too much. Okay? So, we're going to look at a different type of problem, or a different actual application, but same type of problem. So it's again the business world, talking about price, cost, revenue, profit, all that kind of stuff. So companies can make the most amount of money. So companies always want to find a balance between how much of an item they want to sell and how much money they want to make in total. Um, for example, if a company prices an item extremely low, they'll probably sell a lot of that item, but they'll make very little money. And conversely, they can sell an item for a high price, but can probably still make very little money if nobody pays that much for it. Or if nobody buys that product, it doesn't matter how expensive it is, they're not going to make money. So, the basic assumption is the more that you charge for an item, the fewer people will buy it, just in general. So, like, if someone charges more for, or if one place charges $2 for a coffee and one place charges $1, there's just like a common assumption that more people are going to buy the $1 coffee. It might not be true, but just in general, that's a typical rule businesses follow. So let's think about a gift shop on the Outer Banks sees 1,000 customers a week. They have a new souvenir magnet that they think everyone will want. However, their marketer decided that they could expect to sell 1,000 minus 85 X magnets if they charge X dollars for a magnet. So we have kind of a lot of stuff going on here. So basically, they expect to see about 1,000 customers a week. And basically, their marketer gave them this weird expression, which I know is kind of throwing people in the class. And let's see which one I actually used for this problem. I'm going to go ahead and just use 85. That's it right here. And we'll just hope that's the one I used in the recording. Actually, let me check on that. Hold on 1 second. So we are going to use 80x instead of 85, okay? So basically, we want to think about what this expression tells us. Because I've been giving this expression, but what does it actually mean? All right. So let me see if I can. Oh, there's my thought. Okay. There we go. So what that actually means is think about it like slope-intercept form. That 1,000 is kind of like the y-intercept. So if I take, I'm just going to copy and paste it. If I have 1,000 minus 80x, 1,000 is my y-intercept, or my starting value, and my 80, or my negative 80, is my slope. And slope is like an increase or decrease. In this case, it's a decrease. All right? And my x is my price of the magnet. So, let's put this in purple. I'll italicize that because it doesn't really matter. Now I'll do purple. Maybe I'll even bold it because why not? So this tells us that, so the y-intercept is when x is 0. So when they charge nothing, they'll sell 1,000 magnets, which makes sense. Everyone who walks in, free magnet, sure, whatever. I'm on vacation, I'll take a free magnet. They'll sell 1,000 magnets. But if they charge an extra dollar, so for every additional dollar they charge, they're going to sell 80 fewer magnets. So they're going to sell less the more they charge. So like if they charge $1, like maybe 900 people will say, nah, or 920 people might be like, yeah. But 80 people are going to be like, no, I'm all set. I don't know. I'm not going to pay $1 for a magnet. And then every additional dollar decreases the price by 80. All right? And you can see how eventually they're going to charge so much that no one's going to buy it. All right? So we're kind of going to see all that in this problem. So hopefully that makes sense. Okay. So I want you guys to try to figure the table. That's a very important thing to do on your own. So I want you really to fill in the table to show the predicted number of, oh, I didn't change it from downloads. Dang it. Predicted number of magnets. I'm glad I'm doing this before the live. At each listed price. Then find the revenue at each price. So the first row, we're just doing, the first row's been done for you. If they charge nothing, everyone's going to buy it. They're going to make no money. All right? You're going to have to write in the expression for the number of purchases, but it's written right above. Okay? And they give you the prices. You'll notice that one of these prices, something funky happens, which is what we're looking for, okay? So take a minute, pause the video, and fill in that table. Okay, so here's our table. The number of purchases, as you'll recall, is that expression up above, that 1,000 minus 80x. 80 fewer purchases per each dollar. So we see that the more they charge, the more the price goes up, the fewer people that buy it. And you'll notice, 15 bucks, no one's buying that magnet. Like, I mean, I probably would because I'm a weird tourist, but whatever. They're predicting that basically no one's going to buy this magnet at that point. So at some point between 13 and 15 people, no one's buying this magnet. And the revenue, you'll notice, they start off making like 2,000, then they're at like 3,000, and then, hold on, I probably did this wrong because it doesn't make any sense. Let me check my math real quick. 8 times 360, 2880. Oh, this one's wrong. That's why. Okay, we're good. All right, sorry. I did my math wrong. Okay, so yeah, we have all our numbers here. The revenue goes up, but then it sort of starts going down again. So we see that maybe they should be charging around $5 per magnet. And we'll see our graph later will give us a more exact answer of how much they should charge per magnet. And we'll just have to see what that looks like. Okay, so we're going to go ahead and go to desmos.com/calculator to graph the function. It's a hyperlink. You should be able to click on it and go there. Let's do that. So now I'm going to type in y equals, and let's see, y equals that. I can copy and paste because it's a Google Doc, and Mr. Roboto didn't mess it up today like I did last week. That was a royal circus, wasn't it? So I'm graphing that, and oh look, the graph looks weird. Sorry. Oh look, the graph looks weird. So we have to change the window. So remember, you have to go into the wrench over here, the graph settings, to change the window. Otherwise, this graph looks terrible. In order to do that, we have to sort of see what the heck's going on here. So if I scroll to the right, I see, oh geez, something happens over here. So I'm actually going to make my X window stay the exact same, because my X-axis, I'm seeing what happens. It goes up vertically, and then mysteriously in the future, it goes straight down. All right, and that's because our numbers are so small. My revenues in the table, remember, were in the thousands. So I'm going to go ahead and let's see, what was the highest revenue I saw in my table? I saw up to 3,000 in revenue. So I'm going to go ahead and make my graph, I'll be optimistic, I'll make my graph go up to 4,000. So my x-axis was fine. I'm going to change my y-axis. So the upper number goes up to about 4,000 because I'm optimistic. Okay? And now at this point you can click and drag so it really fits well so you see your numbers nice and clearly. That's why it doesn't super matter what window you pick at first because you can always change it. So now I see my graph. I've got a lot of important information on this graph. So let's see, what does it want me to do with my graph? Oh, that's the wrong one. Okay, so let's see. What are the zeros? I'll just type the equation actually really quick. Y equals that. So what are the zeros? The x-intercepts. Those are really important points. Remember, zeros are the x-intercepts. There are going to typically be 2 of them. There might be 1 and there might be none. But that's more for later lessons. So my zeros, I need to look at my graph, and they're already marked with the gray dot. If you hover over the gray dot, it tells you what the zeros are. 0 and 12.5. All Alright, so 0, 0, and it's 12.50. Now, what purpose do they serve? The purpose of the zeros is a crucial thing to understand, because otherwise we're just graphing random lines that don't do anything. So we want to think about how we're going to fill in this sentence to make the zeros make sense. I gave you sort of a sentence starter. So if they charge more than blank, but less than blank, the gift shop will do something. So something happens between the two zeros. So if they charge, let's see, this is the lower zero, and this is the higher zero. So if they charge more than $0, if they charge money, but less than $12.50, then the gift shop will do what? The gift shop will earn revenue. Okay? Which, okay, cool. That's helpful. We have to charge something less than $12.50 to earn revenue. But really they want to know, how can they possibly earn the most revenue possible? So if they look at the vertex, this isn't part of the question, but just a bonus for you. The vertex is, let's see, it's my highest point. The other group, my vertex is 6.25, 3,125. So 6.25, 3,125. So that vertex says that charging 625 will give the most revenue at $3,125. So really want to make sure we're looking at that revenue, figuring out, okay, we want to make as much money as we possibly can. How are we going to do that? And that's by charging $6.25. The vertex always tells you the best option or worst option. Okay, so then, other things to consider. The gift shop also has to consider the cost to make the magnets. Magnets don't grow on trees. That would be weird. The gift shop has to consider the cost. If revenue is more than the cost, if they make more money than they lose, then they earn what's called profit, which is like really the goal. That's why companies can make all the money they want, but if they're spending more than they make, that's what causes them to go under. That's why companies that charge a lot for things can still go bankrupt, because they're not earning enough to pay for their costs. So they could charge anywhere between 0 and $12.50, but they might not actually end up earning any profit from this. So we're going to go ahead and we're going to graph this line as well. We're going to graph that, and we're going to see what the zeros are. I'm just going to graph them both together because that's fun. So now we're going to see what the zeros are here. Well, now my graph's in blue. And notice, I have much fewer values for where I'm actually going to be earning profit. I'm only earning profit if I charge, let's see, between $3.46 and $9.05. So I have to charge between 3 something and 9 something in order to earn a profit. All right, and the reason for that is, even though like $10, even though I'm selling it for more, I'm not expected, remember, to sell as many, because I'm selling 80 less per additional dollar. So I'm selling less of them, and that's making a difference in my profits. So, let's see, where the heck were we? Ah, the zeros, yes. They were, oh gosh, 3 point something and 9.0450. I gotta check that 3 again. 3.455. That's almost what I wrote. Whatever. 3.455. So really $3.46 and $9.05. Okay, so that's that zero. And what purpose do they serve? Again, it's a very similar question, but notice it's a more useful one. If they charge more than $3.46 per magnet, but less than $9.05 per magnet, the gift shop will earn profit. Okay, they will earn money. Okay? So that's really the goal with that. Really wanting to make sure we're seeing where the vertex is on the graph, where the zeros is on the graph, where the zeros are, and being able to tell you, why do I care about those points? What do they tell you? All right? You'll also notice that even considering the cost, Notice my vertex is still at 6.25. The vertex did not change because it had the highest revenue there, so it's still going to have the highest profit there. So the purpose of the vertex didn't really change. All right, so the next part of this is going to focus on the next type of questions you're going to see on your review today. Okay, the next thing we looked at, which I think went pretty well based on what I remember from the exit slips, was multiplying expressions where there's two things being added together. So like distributing, it's kind of like distributing twice basically. And remember, we modeled those with an area diagram. So basically one side of this rectangle was x squared plus 1. And the other side of the rectangle was 4x plus 5. And then basically figure out the area of each of the four sections. And we had a little analogy to help you keep track of everything. Multiply the first terms and the outer terms, and the inner terms and the last terms. So basically, x squared plus 1 gets multiplied by 4x. And then x squared gets multiplied by 5. And then the inner terms. The 1 gets multiplied by 4x, and the 1 gets multiplied by 5. So really, there's two different trains of thought. You could also just say, distribute the x squared, then distribute the 1. And the key to remember is you will have 4 terms to add together, and you might have to combine like terms as well. So if we multiply the first terms, the x squared times 4x, we get x squared times 4x, and then we got x squared times 5, and then we got 1 times 4x, and then 1 times 5. And all those terms get added together. So 4x times x squared is 4x cubed. X squared times 5 is 5x squared. 1 times 4x is 4x, and 1 times 5 is 5x. I'm sorry, 5. So let me just add all 4 of those together, and we have our solution. And this one we have no like terms to combine, and they're all nice positive numbers. 4x cubed plus 5x squared plus 4x plus 5. Alright, so there's that first one. And I'll put that in red, so that's the answer. And again, you don't have to use the area diagram if you don't need to. It's just there to help you remember those 4 pieces and what those 4 pieces all look like. Alright? Like that next one. The first terms, 3y times 2y, 3y times 2y, and 3y times negative 5, and then we're distributing to 7. So 7 times 2y, and then 7 times negative 5. Alright, so that gives us 6y squared minus 15y plus 14y minus 35. And then those two terms can be combined. Just going to highlight those to show that's what we're changing. And that's going to give us, I'm going to copy the whole thing because I'm lazy. That'll give us 6y squared minus 1y minus 35. Alright. So there's that one. And the last one I'm showing you because something very interesting happens with the last one, and it only happens in specific cases, which is always fun to look at. So multiply this last one. So 5a minus 8 and 5a plus 8. So we're going to distribute that 5a first. So 5a times 5a, and then 5a times 8, and then negative 8 times 5a, and then negative 8 times 8. And some of you thinking ahead might think you see where we're going with this, and you're probably right. 5a times 5a is 25a squared. 5a times 8 is 40a. Negative 8 times 5a is negative 40a. There's a red flag there. Negative 8 times 8 is negative 64. So then when I combine these like terms, I get 25a squared plus 40a minus 40a minus 64. And then, okay, these are some like terms I can combine, and when I do that, 40a minus 40a gets me 0. So I've actually just got 25a squared minus 64. So interesting. The middle term entirely canceled out. And we'll look at situations where that always happens, but that's what's going to happen there. And the structure of this is what happens there, or that's sort of why it cancels out. All right, there's a couple on the homework about how to do that. I'll just highlight the right answers in red so you can refer back to it when you are done. And then we'll do the very last part of our video. Okay, so when you take high school physics, I really hope your physics teacher appreciates that you still remember all these formulas and all the good things about it, because this comes up in elementary physics. I remember doing it when I was in physics, and it's all coming screaming back to me. So just to review what these equations look like real quick, what each piece of the equation looks like. The following equations model the distance in feet a moon rock is from the surface of the moon after t seconds. So that's this one. This is your moon equation, all right? So I'm going to make it gray because the moon is gray. Oh, I highlighted it. I don't want to highlight it. I just want text. Shit. Okay. I'll make it gray. Okay, that's better. Gray. That's legible. And the other one shows the distance in feet an Earth rock is from the surface of the Earth after t seconds, or you could just call it a rock, because that's what we do here on Earth. So then I'll make that one green because the Earth is green. Actually, the Earth is mostly blue. I'll make it blue. All right, there's Earth. So from the equation, how fast was each rock thrown? Let's see if we can recall that the speed, or the initial velocity, or how far it's thrown, is represented the linear term, 32 feet per second. And that's for both of them because they both have that 32t in there. So I'll put that in red. How high were the rocks thrown from? They were both thrown from that +6, that y-intercept of 6. They're both thrown from 6 feet up. And we have to graph both functions and see how we can see from the graph that gravity on Earth is stronger than the moon. Like you've probably seen those videos of like astronauts jumping on the moon or walking on the moon. They sort of float sort of gracefully, they walk, but they're like in the air for longer. It takes them longer to reach the ground on the moon because gravity isn't as strong. So I'm going to go to Desmos, which I just have open on my computer at all times now. That's just what I do. That did not work. Hold on. Did I even copy it? Oh, jeez. Okay, let me copy it. Let's copy it correctly this time. Copy. There we go. Okay. I need to change my window, clearly. Let's see, it's not terrible. Okay. Oh, you know what's happening? That's not an exponent. A couple things on Desmos. Make sure you're definitely using exponents. And make sure also you're not using commas. Okay, do not use commas on Desmos, because it'll think you're trying to write an ordered pair, unless you're plotting a point, which you're probably not going to do. Like if you're writing, well, cool, that's calculus. Okay, yeah, unless you're plotting a point, which you're probably not going to do. And my formula, that's much better. I'm just going to click the zoom in button. That's a little bit okay. I'm just going to change the window. Let's see. I'll just make it top out at 100 on the y-axis. Seems like it'll work. Yeah. So I'll just move. Okay. So there's my Earth. Can I change the color? Yeah, I'm going to make it blue to match the other one. Then I'll have moon. Wait, is that Earth or is that moon? That was moon. Dang it. Okay. Alright, hold on. Oh, I'll make it black, I guess. Now I got Earth, which was this one. Copy, paste. Yeah, make good use of copy paste. Nope, that was wrong. Squared. Okay, that looks right. Why do you hate me? What's wrong? Implicit equations of x. I don't even know what that means. Okay. That's better. Let's use y. If your graph doesn't show up and an exclamation point shows up, just try to read that and see if it makes sense. That didn't really make sense to me, but just use a y. Okay, so now we see that this Earth graph, this red graph, I'll make it blue to match, seems to have much sharper curve. It goes down a lot faster. So that rock, if you throw a rock at 32 feet per second straight up, it doesn't seem like a terribly fast throw. It's like pretty reasonable. And you're 6 feet tall, so if you're not like me, you can expect the rock to hit the ground after about 2.17 seconds. And then the moon rock, if you throw that rock on the moon, you don't expect it to hit the ground for 6.25 seconds. So it hits the ground for more than 6 seconds. So, going back to our task statements, gravity on Earth is stronger than the moon. How does the graph show this? Well, Earth's rock hits the ground sooner, or it has a smaller zero than the moon's graph, and a sharper curve, which means gravity is pulling it down faster. Alright, so gravity is that force acting total opposite. You throw the ball up, gravity is constantly pulling it down. So that's the graph sort of shows you that. So just make sure when you go to do your forms today, you have this in front of you. It'll refer back to this a lot. It won't be asking you the exact same questions, but if you've been following along, if you have the graphs made, it should be much better today. And since we are moving towards a pass-fail system, it is a 9-point form, and you have to get 6 points to get a pass. You are still allowed to do revisions, but if you get below a 3, even a revision won't get you to a pass. So keep that in mind. Don't just be blind guessing. If you have questions, email. All right? We'll also be setting up a Google Meet at some point on Wednesdays for like just office hours, like a type of enrichment thing, and we have our live as well this morning, unless you already missed it. All right? So best of luck with that, and have a good day.